Hi students, so let's revise our Bohr model spectrum through another DPP. There are 4 questions, so let's start with the first one. The third line of Balmer series corresponds to the following change in the angular momentum for an electron. See, first of all, we have to draw what is happening. See, this is the second state, then this is the third state, this is the fourth state, and let's say this is the fifth state. If you really want that, this is the ground state also. So let's say these are the states. Now let us name them. Ground state, this is the second state, third, fourth, and fifth. Now question is saying third line of Balmer series. The Balmer will end here, and third line, the first line, second line, and third. So this line will correspond to the third line of Balmer series. Now question is asking what is the change in angular momentum. We know that angular momentum is given by quantization that was stated in Bohr's model postulate, that is nh upon 2 pi, right? Now wherever the n is changing, angular momentum is changing. So you see n here 5 to 2. So what is the change in n? We are talking about the magnitude only. So that is 3. So 3 gets multiplied to this. So that will give you 3h upon 2 pi. That's a change in angular momentum magnitude wise. That's a good question. Now let's come to the second. It is saying how many types of spectral lines of photons you can call are emitted from a mixture containing hydrogen in second state and helium in the third excited state. So let us visualize where the atoms are. See, this is let's for hydrogen, right? So hydrogen is present in the second state, and let's see for helium. Helium is present in the third excited state. That means it is present in the fourth state. So let us now individually count all the photons and then see how we can go ahead. So let's go ahead on this. Hydrogen is present in the second state. So it will give us only one type of photon. So let's number it 1. So we are getting one photon, one spectral line from H. Now let's count for helium plus. So helium plus is present in the fourth state, that is the third excited state. And clearly you know this will give how many lines? This will give 6 lines. There is a formula also, n into n minus 1 by 2. But yes, so we have 6 lines from helium and we have 1 line from hydrogen. Now, should we add them? No, we have to check one important thing, and that is this. Students can easily verify the transition which is 2 to 1 in hydrogen is basically matching 4 to 2 in helium. So this photon is common with this photon. That means we don't have to count this. It is already present here. So it will give us 6 independent photons. So that's good. Now let's come to the third simple question, which is not correctly matched with respect to the region of electromagnetic spectrum. Lyman belongs to ultraviolet only. That's okay. Balmer belongs to visible only. Let's verify this. Passion belongs to IR only and bracket belongs to IR only. These 3 things are fine. I am having some doubt in this. We know that in Balmer, when you come to 2, so the 4 lines only are there in visible range. Students should understand this. In Balmer series, lines corresponding to transitions like this: 6 to 2, 5 to 2, 3 to 2, 4 to 2, and 3 to 2. These 4 lines are invisible and rest will be in definitely ultraviolet. So visible only is the wrong thing. So Balmer contains visible as well as ultraviolet. Now let's come to the fourth important question. In order to obtain all the lines for d excitation from n equal to 4, how many minimum number of hydrogen atoms in a sample are required? So that's a tricky kind of question. Let us first of all clearly understand it. So let us draw the various orbits 1, 2, 3, and 4. And let us see the lines there. So these are the lines 4 to 1, then 3 to 1, then 2 to 1, then 4 to 2, 3 to 2, and finally 4 to 3. We can clearly see there are 6 lines in this, right? But we also know that some atoms can give more than one lines. So surely we do not require 6 atoms. So let's say one atom will be completely used for this, because when it comes to first state, it will not go up again. That means 4 to 1 will be given by one atom only. Now you can see this. The atom which is giving 4 to 3, right? Let's say this is a second atom, can also give this 3 to 1. It will come from 4 to 3, then it will come from 3 to 1. So second atom can give this. Now let's this. Third atom, if atom is giving from 4 to 2, then it can also give 2 to 1. So this is the third atom. And you need a separate atom for this, right? So you can clearly see some atoms are doing more than one lines and some are exclusively giving one line only. So we can count minimum 4 atoms you should require in this thing. So that's a good revision. Thanks a lot.